Greetings! In this video, we will be covering the part 6 of CMP 1002 Object-Oriented Programming course. Here, we will be talking about memory allocation, specifically the stack and the heap, as well as we'll talk about the new and the delete keywords, the operators. So one of the things that we haven't talked about so far is when you are running a program, where does our program live in the computer? So the short answer of this question is the computer's memory, the RAM or the read access memory. Whenever you have a file, a CPP program, a code, when you build it and compile it and then run it, the executable of this program will be uploaded, will be copied, I can say, within the computer's memory, the RAM. Specifically, what is called the program memory within the computer's memory. Because, as you know, multiple programs are being running within the computer's memory. For every single one of these programs, it has a specific program memory, which has a start address, which has an end address. And within this program memory, there are a couple of segments or like little groups called code segment, data segment, BSS segment, and very important two things called the call stack and the heap. Let's briefly look at the three segments first of all. The three segments, the code segment is where the code of the program is located. When your executable is copied into the RAM, the actual code, all the declarations, the ifs, the for loops, the function declarations, classes, all of them are located in the code segment. This is a read-only area. Unlike all the other segments and the heap and the stack, this is a specific area where you cannot write something on. It is only readable. So therefore, it's kind of like secured because you cannot change the code while the program is running. And also, it has a fixed size. The data segment is where your initialized global variables, constants, statics are located. This is a read-write area, so the values of these global variables may change based on your code during the lifetime of the program. Similar to the code segment, the data segment has also a fixed size. The third part, the BSS segment, is very similar to the data segment. The main difference is the fact that this is where the uninitialized global variables live. Other than that, it has the same features as the data segment. It is again a read-write area, so the values of these global variables after a while will be initialized. Some values will be copied inside, and still these things will be living in the BSS segment. Considering such a very small program, all this code is going to be copied inside the code segment. Then these initialized global variables, gvar, gnumber, pi, they will be copied inside the data segment and they will be living inside the data segment. The last two items, the h and br and the gbr, are, as you can see, are uninitialized global variables. So they will be living in the BSS segment. I will not go over the details about these segments any more than this. There are more details, don't get me wrong, but these things will be covered in much more detail in the operating system course, in the memory management part of the operating system course, so I'm not going to be continuing in more detail about these parts. But what we will be focusing in more detail are the stack and the heap. Stack is basically where your local variables live. When you declare any local variable like int I, int x, double d, char ch, something within a function, but not global variables, be careful. Global variables are for the data segment and the BSS. The local variables live in the stack. Stack has a very limited size, a couple of megabytes, depending on the hardware and operating system. It provides fast access to all the values inside, due to this very organized, simple data structure, this last in, first out system. In addition to the local variables, when you are switching between functions, the return address of the caller function is also written inside the stack. What I mean by that, just give me a sec. Give me a couple of slides. Another super important thing is that when the function where the local variables are declared ends, these variables are automatically deallocated by the compiler. So for any variable that has been declared within the stack, you don't have to think about deallocating them at all. This is gonna be done automatically by the compiler. The stack will has an initial size based on how many things that are being inside, and as the program continues, it will grow or shrink, but there's gonna be a maximum stack size, and it's gonna be a bit of an issue very fast, very soon. The second part is the heap. This is, unlike the stack, a very big memory space. It is generally all the memory you can use is the heap. Depending on the operating system, it can give you gigabytes of memory, depending on how much RAM you have and the policies about the operating system. All the dynamic memory allocated variables via the malloc, realloc, calloc, new, all those things are located in the heap. But be careful. If you are declaring a pointer and then using the malloc new and allocate a memory, this memory is gonna live in the heap, but the pointer itself is still a local variable. It's gonna live in the stack. Heap has a couple of different organizations. It doesn't have a specific single data structure. It can have options depending on the operating system, but generally they are slower in terms of access than the stack. Although it has a super good size, the downside of the heap is not just being slower than the stack, but also any variables that you have declared in the heap should be deleted, deallocated manually by the coder, using the free, delete, these kind of keywords. So let's look at this last in first out system of the stack. Stack has a super simple data structure, and it has at its core two key functions. An item can be put inside the stack via the function called push, and an item could be taken out of the stack using this function called pop. Whenever you put something in the stack using the push, it's gonna put the item into the top of the stack. Always. So you cannot insert something in the middle. You can only put something on the top of the stack. In reverse, when you're taking something out of the stack, you can only take it out from the top of the stack. So considering a very short code, I intentionally put down some line numbers just to differentiate between different lines. In the beginning, the int x will be allocated, will be pushed down into the stack using the push function, because it's the first local variable defined in the main. Next is gonna be the double y, with its values, of course, 4.56, followed by the char ch, with its initial value, capital A. Then, as you can see in the code, there's a function call. So this is something very interesting. When you have a function call, you, as you can see, will jump to line number 1, the square function. But the thing is, at the end of the function, the program should somehow know where should I return to. In this example, it's clear that it's supposed to return back to line number 9. But how is he know? The program should know that it should be returning back to line number 9. The easy answer is, it's gonna put a little return to blah blah, the return to note inside the stack. So he will know that he should be returning to this address line number 9. Then we jump inside the square function. Inside the square function, there's a single argument called s. So it's gonna be a local variable. It will be pushed down the stack. And finally, inside the square, there's one more variable called result, which is gonna be pushed down to stack. And the values of the s will be taken out. They will be multiplied, put inside the result, and the result will be pushed up to whoever is calling this function, in this particular case, the main. So at the end of this square function, the result will be popped back, s will be popped back, and then he will now see that he's just supposed to return to 9. And he's gonna return to 9. And the result value of the function is gonna be copied to the variable x. Then at the end of the program, at the end of the main function, all these three variables will be popped out from in the reverse order: the ch, the double, and the x. So this is basically how the stack works. Because of this pop push systematic, it's very fast. It's very flexible. A little bit of a comparison between stack and heap. Stack has a linear data structure, whereas heap generally has a hierarchical data structure. Again, similar to the segment stuff, I'm not going to go into the details about the hierarchical data structure of the heap, because there are multiple versions you can implement the heap. And also, these things will again be covered in the data structures and algorithms course in much more detail. Generally, access to heap is slower than stack. But since we are dealing with the memory again, this is not going to be that slow, don't get me wrong. But still, it's going to be a little bit slower than the stack. All the local variables will be living inside the stack, whereas dynamically allocated variables will be living inside the heap. Stack will generally have a very short, very small limited size, whereas heap generally doesn't have a specific limit. The hard constraint is going to be the size of your RAM and the policy of the memory allocation policy of the operating system that you are using. Stack variables will be automatically deallocated, whereas the heap variables will be manually deallocated by the programmer. Due to this limited size, stack will have what I will be calling a stack overflow problem. You can just overflow the stack. You can practically push more items than there is space in the stack. In that kind of scenario, stack will overflow and C++ will give you a very specific error. In the heap, generally you don't run out of heap, you don't run out of memory in the heap. But what you can do is, if you don't do the manual deallocation, some parts of the heap may be allocated even after it is completely pointless to use this memory allocation. So the program is not going to be utilizing this memory allocation, but since you forgot to deallocate this memory, some part of the memory is unusable. This is called the memory leak issue, which is again going to be a super big problem. Okay. Let's try to find the size of our stack in our particular computer. So let's try to open up a very big array in the main. An int array of size, let's say 1 million. So here, I'm just going to say int array 1 million. Am I wrong? Nope, that's fine. Let's run this code and see what happens. So it takes quite a while, honestly. So he's trying to allocate a lot of things. And at the end, he says process finished with exit code -107,374,1571. This is the stack overflow problem. A very specific code down there. Because if I just delete it and reduce it down to 100,000, it's not going to give us the same error. It's going to finish with an exit code of 0, which means there are no problems in the code. So let's try the same thing with a double array. Because in integer, I think I can open up an integer array of size 300,000 in my computer. Yes, I can. But what if I change the value to, change the variable type to double? Okay, so it's gonna still again give me a stack overflow problem by the look of it. Yeah, it did. So the thing is, if you remember the CMP 1001, different variable types have different, individual items have different sizes. Integer generally has like 4 bytes, whereas double is gonna have like 8 bytes. Again, this depends on your hardware and the compiler. But in this case, I think in my computer, the int is gonna have like 4 bytes. Therefore, if I try to open up a 1 million integer size array, it's gonna need 4 megabytes of memory, but my stack is around 2 megabytes as far as my previous tests, so it's not gonna be possible. So that is the stack overflow problem. So if you put a lot of items in the stack, then you will very fast run out of space, and the compiler will give you a very specific error, this stack overflow error. In my computer, apparently in using MinGW with Windows 10 64-bit with a 64-bit hardware, the stack is around 2 megabytes. So the biggest array that I can open up is around 519,100. But again, this can depend on the hardware, operating system, and the compiler. Okay, after this discussion about the stack and the heap, let's look at the new operator. Unlike the malloc, new is actually not a function, is an operator. And the job of the new is it denotes a memory request in the heap. So you are saying to the operating system that, can you allocate me a memory in the heap whose size is 10? If the memory is available, it will initialize the memory and return the address of the newly allocated initialized memory to a pointer. So the zeroth item of this 10 integer, let's say, array or memory slot will be returned back as the return type of the new operator. And therefore, I'm just going to put it inside this integer pointer. If I open up a double array in the heap using this new double 15, then the return type of this new operator is going to be a double address, which can only be kept inside a double pointer. If you go for the classes, nothing is so different. Let's assume that this ice vehicle class that we have talked about in the part 5 lecture, I'm just opening up an object from the ice vehicle, and again, he's gonna allocate that memory in the heap, and he's gonna get the return address of that. He's gonna get the address of that object back as the return type, as a return value, which will be kept inside this ice vehicle pointer PV. One thing of note is the fact that in all these three scenarios, the pointers themselves, P, Q, and PV, they are local variables. Hence, they will be inside the stack. They will live inside the stack. On the reverse side, the delete operator is used to deallocate the previously allocated memory at the heap. So it's basically saying to operating system that you can, I stopped using this memory slot. You can reuse it for whatever purposes you want. Another application or another memory opening up another new operator within the same program, whatever you want. It's completely up to you. So it's a bit simpler than the new. Okay, based on these things, let's have such an example in which we define a class, and then we will be using the constructors and destructors, and we'd like to see when these constructors are called, when we are opening up an object, when these constructors are called, when we are using the new keyword, and similarly when the destructor is being called when you use the delete operator. So the example says define a class called tank, having a single member field and 3 functions. The member field is going to be protected int armor rating, which is going to represent the armor, or you can say the life hit point of the tank. And there's going to be a constructor which takes single integer, which is going to be the value of the armor rating, and initialize the object. Also, I'd like the constructor to write down such a line: constructed tank object -1 parameter constructor, and armor rating is whatever the value of the armor rating of that class, of that object is. Next, I'd like to have a default constructor which sets the armor rating to 0 and print out the same thing. The only difference is gonna be that instead of saying 1 parameter constructor, it's gonna say default constructor, and the armor rating is gonna always be 0. Finally, I'd like to write down a destructor which should just print out destructed tank object, armor rating is whatever the value. Okay, class tank protected int armor rating. Then public for the constructors, tank int armor rating std code, what should I say, constructed tank object, one parameter constructor, comma, armor rating is armor rating std and l. Similar to this constructor, I will be having a default constructor which is not going to take any parameters. So it's going to say armor rating equals 0, and the rest is going to be very similar. The only difference is going to be to say default constructor. Finally, I will be having a destructor using the tilde in front of tank. Only a printout will be here, and it's gonna say destructed tank object. Since there can only be a single destructor, that's the end of it. So let's continue. He says in the main, initialize one tank object called 5th division tank with a constructor of 20 armor rating, a second tank object called 4th division tank with a default constructor, and a third tank object using the new keywords, the new operator of 30 armor rating, and assigned to a tank pointer. And at the end, we shouldn't forget to delete to call the destructor of the third tank object at the end of the main. Okay. So this is no longer necessary. Tank, what's the name? 5th division tank. Open up parentheses. What's the value? 20. That's it. Next, 4th division tank, which is not going to take any parameters because it's going to call the, I'd like it to call the default constructor. And finally, tank pointer, PTR 3rd division tank equals new tank 20. Should it be 20? 30. Finally, at the end of the code, he says delete PTR 3rd division tank. Let me run this code and see which one of these constructors are being called where and when. Okay, so the first line, line number 20, tank 5th division tank 20, is using the one parameter constructor. Why? Because I have given him a single parameter, a single argument. Therefore, he's going to use the normal one parameter constructor. Whereas in line number 21, I did not give him any value. Therefore, he's going to use the default constructor of the class. The third is going to be similar with the line number 20's 5th division tank. It's going to be calling the one parameter constructor. And at the end of the program, all three of these objects are going to be destructed. The 5th and the 4th will be destructed because they are local variables. They are variables in the stack. So the operating system the compiler will automatically delete them. For the PTR 3rd division tank, the object that has been referred to by the PTR 3rd division tank will be destroyed because of this delete line. If I comment this out and I run this, you will see that there are only 2 destructor calls, because of the object referred to by the PTR 3rd division tank is not destroyed explicitly. You see? Now we have 3 constructions but 2 destructions, which is gonna cause you a memory leak. Maybe not in this simple example, but in many cases it's gonna give you a memory leak. So let's do a little bit more additional stuff with the tank. So here we have to add 2 more functions to the class tank. The first one is called the void sustain damage, int damage. It's gonna simulate the tank gets hit by a damage, some damage source, we don't care, and it should decrease the armor rating of the tank by the damage amount. And second function should be void evaluate status that reports back the status of the tank. If the armor rating is greater than or equal to 0, then it should say the tank is operational. Otherwise, it should say the tank is inoperable. Also, write a function outside of the class called void inflict damage, int damage tank t. That takes one int value and a tank object, and it's supposed to call the sustain damage function of the tank object t with the damage value. In the main, we'd like to call the inflict damage function on the 5th division tank object. So first of all, let's write down the sustain damage and evaluate status functions. So they are gonna be public functions, so they will be continuing after the destructor. Void sustain damage, int damage, and tank t. No, just int damage, right? Yep. Armor rating equals armor rating minus damage. Simple as that. Then let's write down second function. Evaluate status. Here it's gonna supposed to say if armor rating is greater than or equal to 0, then it should say std code tank is still operational. Operational. Yep. Else inoperable. Okay. And outside of the class, outside of the main, we'd like to write down one function called inflict damage. It's gonna take int damage tank t, tank with capital T, of course. Then here it's gonna call the sustain damage function sustain t dot sustain damage. And then I'd like to call the inflict damage function on the 5th division tank object. So let me comment these things out because they are not necessary for our discussion. Same stuff, the delete is also gone. Inflict damage 10 5th division tank. Okay, so the tank has been initialized and one parameter constructor is being called, and then the tank is being hit by 10, and at the end it's been destroyed by, oh wait, what is going on here? Wait, there I'm seeing two destructed lines. How does it happen? There's only one constructed call, so one object should be called. But for some particular reason, two objects have been destroyed. One of them having an armor rating of 20, another having an armor rating of 10. Okay, what is going on here? This looks very, very interesting and suspicious. The thing here is the fact that when I am passing the class, the object to the function, C++ sends a copy of this 5th division tank to this inflict damage function. So in the function, the T is another object of the tank class T, of the tank class. So T is one object, 5th division tank is another object. But so their values, their armor ratings are actually gonna be the same. And there's gonna be a temporary variable being constructed, and it has been destructed. So this is the destructed call of the temporary object, whose armor rating is 10, which is reduced by 20 minus 10 is 10. And this is the destruction of my actual 5th division tank object. So I can do a little bit of I can put a little bit of code here, end of program, just to clearly see that where this first destruction comes. So as you can see, this destruction is an automatic destruction at the end of the program, because fifth division tank object is a local variable, so it is being destroyed at the end of the function. But apparently, the inflict damage function is opening up another tank object whose value, whose armor rating is the same as the fifth division tank, and it is being destroyed at the end of the inflict damage function. That thing, we cannot call the constructor, we cannot see the constructor of that call, because this local variable t is instantiated via a special constructor called copy constructor. So far we haven't seen what is this copy constructor, but this is gonna be a quite important thing in the subsequent weeks. Okay, so that's gonna be it for this part. So next week we'll be going deeper into this copy constructor, and then we will continue with the smart pointers, the unique pointer, the shared pointer, and the weak pointer. Thank you for listening. I hope it was a educative video. See you next time. Goodbye.